So it is my pleasure and honor to introduce our distinguished Kavli Nanoscience Institute speaker today, Professor Martin Wegener, did I pronounce correctly, from the Karlsruhe Institute of Technology. So it's a little bit, I actually see a lot of parallels between California Institute of Technology and Karlsruhe Institute of Technology, who he has been a professor of applied physics there since 1995, so he must really like it there. It's a very long time. And also the director of Institute of Nanotechnology. I guess it's kind of like a sister to the KNI. So Martin has many distinguished awards, and I think I would like to begin with the one that I find near and dear to my heart, which is where's the technology? Yeah, the SPIE Prism Award 2014 for the startup company named Nanoscribe. So how many of you have ever used a Nanoscribe instrument in your life? You've actually operated it? You've personally, it's probably the most proudest moment for you. So, of course, all of us who have used the Nanoscribe instrument we like it very much, and it's extremely capable and extremely innovative. And the founder of the company and pretty much of the entire two-photon lithography technology is sitting right here with us. So this is a huge honor for us. So thank you for coming here. So in general, I would say that Martin's or Professor Wegener's problems are focused on 3D printing that is induced by laser. So laser-assisted and light-assisted architecting of materials. Specifically, I think your focus has been in photonics, but maybe we'll hear more. I hear the talk yesterday was all on mechanics, so you're a jack of all trades. Martin is a highly cited researcher, and of course we know that because every time we try to do something, there's already a Wegener paper on that. Maybe this is the experience you share with us as well. So you all have read the biography, so I'm not going to go through all the societies and all the national academies that you belong to, and I know you'll appreciate this. But I did learn one interesting fact about Professor Wegener. He does not own a car, and he also doesn't own any rollerblades. So I don't know how he gets to work, but apparently this seems to be working out very well for you. So welcome to Caltech. We're delighted to have you here, and the floor is yours.
Good afternoon. My pleasure to speak about 3D laser nanoprinting. This is a mixture of things, a quick tutorial in the beginning, what this is about and how it works, but at the end I also want to guide you to some things that are pretty new and also show you where the challenges in this field are. So let me jump into things. That's the way how it works. It's very simple. We very tightly focus femtosecond laser pulses into the volume of a photoresist, which can be a liquid monomer. And then by means of two-photon absorption, we induce a chemical reaction in the optical focus, which often, not always, but often brings this liquid monomer into a solid state, into a cross-linked polymerized state, and then we scan the laser to do whatever we want to do. And at the end, you take a so-called developer, simply a solvent, can be acetone or isopropanol or something simple like that, and we wash out the insufficiently polymerized material, and you get, for example, what you see here. So the basic idea is very simple. It's like writing with a pen of light in 3 dimensions, and you do whatever you want to do. And I'm doing this to embarrass myself for almost 20 years, from which you can conclude that either I'm ridiculously stupid or maybe there are some subtleties in this thing after all. So let me get in a bit more detail here and show you how the focus looks like. If you care, this is for actual parameters, for 800 nanometers wavelength, for numerical aperture of 1.4. This is an oil immersion system, so diffraction limited focusing really. If you really care about the details, this is for circular polarization to not break the symmetry. And that's how the focus looks like in 3 dimensions. These are some ISO intensity contours. If you find that way too complicated to look at, you may want to look at this cut, which you see on the right-hand side. Very simple stuff. A focus of light, and I'm plotting right away the intensity squared because that's how two-photon absorption goes. So if you now ask the question, what is the minimum feature size I can get? A simple way to think about the problem is the so-called threshold model. It's not exact, but it's a very good starting point. And it basically tells you that whenever the exposure dose is above a certain value, the material is sufficiently cross-linked to be not washed out Whereas if the excitation dose, the exposure dose is below this value, below the threshold, then the material is insufficiently cross-linked and it's washed out. Such that if the threshold is like shown here, you get this voxel, as we call it, in analogy to the picture, a pixel, the picture element. We call these things the voxel. It's like an egg, a nano egg, if you want, a little Lego block that we can make, and this thing we scan. Now, the question, what is the feature side and what is the resolution you can get, is actually a subtle one. I want to go through this quickly. There is no diffraction limit for the feature size at all. And there never has been a diffraction limit. And you can see this if I now just reduce the intensity or power of the laser focus with respect to that threshold. A smaller and smaller part is above that threshold, and you can get very small features. In fact, it's not a very big deal, even with a nanoscribe instrument, to get below 100 nanometer size features on a substrate, for example. And in principle, you can keep going and going. And there are even some reports where people show you 9 nanometer lines. But this is totally useless, I would say, because nobody wants to print a single voxel. So at least you want to have a second voxel coming into the game. And that's what I'm doing here. I have now a second exposure, which you see coming up over here. And now I have to make an assumption about the photoresist. And this is important. It's usually a very good approximation to assume that the photoresist just adds up the exposure doses that you have dumped into it. This is not a fundamental law of physics, but this is usually a very good assumption. So I just add up these two exposure doses, and that's what you're going to see coming in from the right-hand side. You see the two individual foci, and now this guy comes closer and closer. Nothing very spectacular happening so far. And what I show here in blue is the sum of these two guys. That's the assumption that I'm adding up the doses. And now if I bring them closer and closer, you see that this minimum becomes less and less pronounced, and at some point this minimum disappears. And technically speaking, this is the two-photon sparrow criterion, and that is diffraction limited. That limits what you can get. The minimum separation is perhaps a bit more than 200 nanometers that you can get. The threshold model would still allow you to get two separate features here, but if you go below this number, actually you cannot separate the features anymore. So for the numbers I'm talking about, the resolution limit, some people call it the Abbe diffraction barrier. That's nonsense. It has nothing to do with that. It's the two-photon sparrow limitation, is 200 nanometers for 800 nanometer light under these conditions. That sounds pretty good. It's quite a bit worse in the axial direction that you can see here. If you have a nicely aligned instrument that is a factor of 2.5 elongated in the axial direction compared to the lateral direction, and the fundamental limit is really a factor of 2. And that basically comes from the fact that you only focus from one half space. You only have the spatial frequencies of half the possibilities, and that gives you an elongation that is at least a factor of 2 larger in this direction than in the orthogonal direction. You could go around this if you have 2 lenses and focus from 2 sides, but typically nobody is doing that really. So if you want to do something more fancy, you can scan a line, for example, and that's a simple thing to do because typically the lasers that are being used have a very high repetition rate such that the individual voxels are very, very closely spaced. Even if you go to very large focus scanning speeds like 40 centimeters per second or so, the individual shots, so to speak, are spaced by 4 nanometers. So that's pretty much a continuous line. You can forget about that. That's very dense for our purposes. If you now want to write, for example, a plane by raster scanning the focus, you have to choose the so-called hatching distance, and this is now already a compromise. If you want to have an optically smooth surface, you want to make this hatching distance pretty small, that you don't see these ripples anymore, but this means you have to scan more often. This means your writing time will go up. Okay, same issue in the third dimension. If you want to 3D print something in the volume, you have to choose the so-called slicing distance. And again, you want to make that fine to get good quality structures. On the other hand, you don't want to make it too fine because then it takes forever to 3D print this thing. These are some parameters that are important in the jargon. So far, I have not actually explained to you why one needs two-photon absorption. And I have encountered many misunderstandings about that, so let me explain. First of all, a little bit of background. Two-photon absorption was first looked at by Marie Goeppert-Meyer in her PhD thesis. She came from Poland and then did her PhD with Max Born in Göttingen and worked this out for atoms. And at the time, nobody cared about this higher order perturbation theory that she did. This went into obscurity. She then changed field, went into nuclear physics, and was the second woman who got the Nobel Prize in physics. And only lately did we have the third woman out of more than 100 Nobel laureates. That's a sad story. And then she came to the US and died. And the picture, I didn't say there's any correlation between these two things. So basically what she investigated is two levels, two energy levels in an atom or whatever, and you ask for two photons, two quanta of light to be absorbed simultaneously. And that's actually a very, very unlikely process. If you ask what is the probability that a photon interacts with a single molecule in my shirt here with this blue color, the cross-section of a single molecule is 10 to the minus 15 square centimeters or so. Very, very small number. So this is like winning in the lottery, the probability of light to interact with any one particular molecule. So two-photon absorption is like asking, I want to win in the lottery in the US and in Germany on the same day. It's a very improbable thing. And that's why I want to show you some numbers here, just to give you a flavor. If you start with lasers that have a fairly low average power on the order of 10 milliwatts or so, even some Chinese forbidden illegal laser pointer can give you 10 milliwatts. That's not a lot. And you use fairly short pulses, 100 femtoseconds or so, you use 100 million pulses per second, you focus it like I described before, and you stick in the number, you get a crazy high intensity in terms of how many watts per centimeter squared you have in the focus. And the typical number is that you get about a terawatt per centimeter squared. That is 10 to the 12 watts per centimeter squared. If this number doesn't mean anything to you, a typical nuclear power plant would give you a gigawatt of power, 10 to the 9 watts. So this means you take 1,000 nuclear power plants and you concentrate this power onto an area corresponding to my thumbnail here. And that would probably hurt a lot if you do that. But the thing is, you only do it for a very short time and in a very small region in space. That's why nothing dramatically happens. But you get a huge flux density of photons per second. And if you now multiply that with the characteristic number in two-photon absorption, which has the units GM for Goeppert-Meyer, we still honor Marie Goeppert-Meyer, and you multiply these two numbers, then you get an area, an effective area, a cross-section that becomes very roughly comparable to this 10 to the minus 15 centimeters squared that you have for one photon absorption. So you need these many photons per unit time and area to make two-photon absorption very roughly comparable in probability to one photon absorption. You have quite some crazy parameters. So I mentioned that this started with Marie Goeppert-Meyer. It actually took 30 years until experiments were done on two-photon absorption by Wolfgang Kaiser at the time at Bell Labs. 30 years later, nobody cared about two-photon absorption for roughly another 30 years. There was no application other than some weird spectroscopy or so. And then it was used actually in the biological context for two-photon laser microscopy. And it took a couple of more years until Soji Maru, who is really the pioneer of the stuff I'm talking about here in terms of 3D additive manufacturing, published a paper using this, and then other groups, and we also jumped onto this. Now I want to explain to you why two-photon absorption is important. First, I show you a simulation here. We want to write a little platelet, and I show you the result for one photon absorption and for two photon absorption. And what you see is that you get huge distortions for one photon absorption, which are simple to understand intuitively. What you have is this focus, this waste of light, and you get a high intensity here, and you get some little tail down here. And if you want to expose a single voxel, that is not a problem. You may have a tail of, say, 1% down here. Who cares? It's not important at all. But if you now start raster scanning and you add up this 1%, say 100 times, then it becomes a 100% effect, and that's exactly what you see here. You get these humongous tails. Whereas the beauty of two-photon absorption, it's very simple. You simply square this 1%, and then it becomes 10 to the minus 4, and then you can add it up, and you get a lot less. Actually, there's still some adding up, which is sometimes called the proximity effect, which is a pain in the neck. It becomes better if you use 3-photon or 4-photon absorption. So the basic trick is just you square the profile and you get rid of the tails. That's the beauty of two-photon absorption. You don't need it if you want to write planar structures. You don't need it for simple lines or something. You only need it if you want to write complex 3D structures where this adding up of the tail is important. So many of you know the nanoscribe instrument. I'm saying this to tell people that I'm biased. I'm excited about this technology, but not because I inherited this company. We were excited from the start. This is what you know. What you maybe have not seen is the generation of instrumentation that has come out last year, the so-called Quantum X. Don't ask me why this name was chosen. This is meant for industrial purposes now, and let's see how that goes. It looks completely different. It's just a big box with a touch screen, and you cannot see anything anymore what is inside there. So the first thing I want to do is show you a couple of examples that you may or may not have seen. And I should like to start with one actually from Nanoscribe, and that is now going into mass fabrication in a couple of companies. And the idea is to 3D print what is sometimes called 2.5-dimensional structures. So structures that you can make a master first, and then you use imprinting, use stamping, so to speak, to replicate the thing. And if you want to do this for optical purposes, the important thing is that you get optically smooth surfaces. You cannot tell from this electron micrograph, but I'm telling you, if you do it right, you can get below 5 nanometer root mean squared roughnesses of the surfaces. So these are by any means optical quality surfaces without any post-processing. And you would be surprised how many companies are interested in making such masters. For example, for smartphones, there's some pretty fancy diffractive optical elements in there even today. But you have to make the master ones. There are pretty fancy micro-optics in car headlights also today to shape the beam. There are arrays of all kinds of lenses. And you have to make the master. You can do this on a wafer scale, and then you use replication. And I'm not sure I'm allowed to say this, which companies this is. This year there will be products on the market made by exactly that technology. So make masters and then use soft imprinting, hot embossing, or whatever for replication. And that's what this Quantum X machine is targeting to do. That's a big thing commercially speaking. But that's kind of trivial in a way. These are structures that are not so impressive to me. This is an example from Harald Giesen's group. This is something you cannot easily replicate, but you can 3D print. He has made these lenses, singlets, doublets, triplets, and you get better and better imaging quality, as you would think from the bigger brothers that have been around for a long time. You might ask, who cares about such lenses? Well, there are no-nonsense applications. First of all, this reminds me to tell you that you can 3D print onto anything, literally. For example, you can print on the end facet of an optical fiber, and that's what's important here. So they are doing this together with a company that builds endoscopes and for surgery. So you want to have something small, still you want to be able to see what you're doing inside of the body. So you need decent imaging quality, and that's what this thing does. It will probably cost, I don't know what, a couple of €100 to make one of those, but for medical purposes, that's actually not an issue. So this will go into applications in a piece-by-piece fabrication mode using two-photon absorption. This is a bit wilder example from Christian Koh's group, where the idea is to print lenses, again with optical quality, to connect elements on optical chips, to shape the beam, to guide it to the third dimension, or to get optical information off a chip into an optical fiber that is next to it. And they have founded a company that aims at doing this on a mass fabrication scale to connect chips to outside housings, which today is done by very precise alignment procedures that have feedback loops in them. And they argue that this will be much simpler with this technology, and there's a lot of money being put in this direction too. This is some stuff we did with Wolfram Pernice. If you care, there are all kinds of optical chips where you have to do testing and you have to couple light from the far field to the optical chip. This is routinely done by grating couplers, which are not so broadband and not so efficient at the end of the day. This cool concept is very simple. It's totally broadband and very efficient. We've called it an Alphorn coupler because it looks like an Alphorn, basically. It's a little lens that you see here, just some support here for mechanical purposes. And then it's a stupid polymer waveguide that is kind of smeared, in this case, into a silicon nitride waveguide. And I would have thought originally that the coupling efficiency is ridiculously low. Actually, it's very high. You can bring the loss down to 0.1 decibel. So in fancy words, this is an adiabatic tapering of this polymer waveguide into the semiconductor waveguide, and it works like a charm. It's very reproducible. And on the right-hand side, you can see that we're not talking about individual elements, but we're talking about making these connectors on a wafer scale. And that's actually no longer a big deal. The last example I want to show you is more a scientific application that we did with Wolf Wulfhegel's group at Karlsruhe. They wanted to convert an STM, a scanning tunneling microscope, to allow them to collect the light that is emitted if you inject current into, say, a single molecule or so onto a surface. And this has been done before. You get electroluminescence, big surprise. And what people have typically done is they have put into the ultra-high vacuum, low temperature conditions an ordinary microscope lens, which is not really compatible with an STM tip in the neighborhood. And then you have to align this thing, this macroscopic objective lens, under these conditions with respect to that tip, which is a pain in the neck, trust me. And the idea was to just get rid of all of this and fabricate a little STM tip by 3D printing, as I explained to you. And it's made such that it's in the focus of a parabolic mirror. This thing is metal coated, silver coated in this particular case. And then it sits literally butt coupled on an optical fiber, on a multimode optical fiber. And then this multimode optical fiber goes from low temperatures here all the way, if you want, to your spectrometer. There is no alignment, no nothing. And this is fantastic. The collection efficiency is much better than what you get with bulky objectives. This thing is very much simpler. And I was afraid in the beginning that they would ask us for 2 or 3 of these tips every day. Actually, they have been using typically one tip for 3 months or so before they crash it because of some accident. So it's actually a very reasonable thing to do. This is more a scientific application. And again, I like this example because I do not know any other technology that would allow you to make such a thing. Okay, so what are the...
What is the scale bar of the actual tip?
The tip has, if you do it right, has a radius of curvature of 50 nanometers or so, but this is actually not important at all. You can even take some normal needle. What they do always is they carefully crush it into the surface, they apply some pulse, and if you do this a couple of times, there's always the situation that one atom sticks out, so to speak, and that's how you get atomic resolution. So they get, I should have mentioned this, atomic resolution routinely with this thing. It helps a bit if your radius of curvature is not so bad, but even if it's hundreds of nanometers, you can get atomic resolution because there's always one atom sticking out, basically. Okay, so this is the old part. Everybody can do this. You get yourself some commercial instrument and you do it. So what are the challenges in this field? And I see 3 major challenges that are not new. I'm just telling you. One is to get finer features. Perhaps you want to have some 10 nanometer resolution rather than this 200 nanometer resolution. And I decided to not speak about that today at all. We did a lot of work over 10 years using stimulated emission depletion combined with this thing to improve resolution. Just for the sake of time, I will not tell you anything about this today, because my experience is that most people care more about making 3D printing faster and scalable. I'm going to say a lot about that. And then also to not just have one dull, stupid polymer, but have different materials, active materials in one architecture. And I'm going to speak about that too. So let me start with faster printing. And one reaction I've gotten many, many times after talks like this is that people say, oh, Martin, this is very nice stuff. You can do things that you cannot do otherwise. But it's very slow, right? I mean, it's this laser scanning. It's a serial process. This is slow like hell compared to parallel approaches like projection-based approaches. Okay, before I tell you my response to this, let's just look at the facts, how things are. And that's how we came up lately with this crazy diagram, which I'm going to open in just a second. But before I open it, I would like to show you what is shown here. So on the vertical scale, I plot the total peak printing rate in units of voxels per second. How many of these Lego blocks I can make per second. And I argue that this is the only meaningful quantity that allows you to compare technologies that have vastly different voxel sizes. Some people use the volume that is printed per second, but that's ridiculous. That favors bad resolution. So I'm not going to do this. I'm going to measure the printing rate in terms of voxels per second. And you see this is a log scale, and I'm going to use this log scale here over 9 orders of magnitude. This is not a small scale. And on the horizontal axis, I plot loosely resolution to the right. So it's the inverse voxel size plotted here to the right. If you find that confusing, you can look at the top. There I show you the absolute voxel size, which increases from the right to the left. We start from 10 nanometer right here, 100 nanometer, and it goes to 1 millimeter. And there are technologies that have bigger voxel sizes. People are printing houses. I do not have that in that diagram, simply. Seriously, there is a...
Do you have a printed house?
I do not have a printed house. And the ones I've seen are not such that I wish to have a 3D printed house. But that's another question here. Okay, so that's what's plotted here. If you don't like these units, I plotted here the rate and how many bits we convert per second. Because that's one of the ways I think about this. The 3D printer is basically a converter of software to hardware. And that's the rate at which we convert a digital blueprint into matter, into something you can take into your hands. Okay, one more thing or two more things. You will see, if you care, lines with slope 3, and these are lines of constant printed volume per second. And in 3 dimensions, in this double log plot, this line has a slope of 3. So just in case you have no idea about these numbers I'm telling you here, let me try to calibrate you with an inkjet printer that you may have at home, a 2D graphical inkjet printer. I don't know exactly what you have at home, but typically they use tens or hundreds of nozzles in parallel, out of which the ink is pushed out. And it's typically done today with photo quality, 600 dots per inch, which is weird to me. This means the pixel size is about 43 microns. And they do this is the number I'm heading at a rate of 10 to the 7, roughly a little bit lower, 10 to the 7 pixels per second. And that's considered fast by many people. At least they buy it and use it at home. 10 to the 7 pixels per second. So now I'm going to open this up for 3D printing, and you see a crazy mess of things. First of all, not so surprisingly, if you look at inkjet printing, these are these triangles here, it's like that. So inkjet printing of 3-dimensional structures also comes at a rate of a maximum of 10 to the 7 voxels per second. This data point here is some former HP Labs printer, actually for a couple of $100,000 price or so. And they use 15,000 nozzles in parallel, out of which the ink is extruded. So each individual nozzle is actually not so fast. It would be lower by 4 orders of magnitude. You would be up here, but they bring it up by using so many nozzles in parallel. And then you see all kinds of different colors. And let me come to the presumably very fast parallel printing approaches, like projection microstereolithography, where you project an entire image into a certain plane. These are these green points here. So here we are talking net 10 to the 3 voxels per second, not so fast actually printed, and the feature sizes are between 10 and 100 microns, minimum feature sizes. There was a big fuss some years ago about this continuous liquid interface printing, if you know that. That's a variant of a projection-based method. That's in a way better, it's faster, goes to 10 to the 5 or 10 to the 6 voxels per second, but you lose resolution. You're rather talking 100 microns minimum feature sizes or voxel sizes. Or if you care, last year there was a nice science paper introducing computed axial lithography. That is a way where you project from different directions two-dimensional images, and you pre-calculate these images that the accumulated dose gives you a three-dimensional exposure profile according to your wanted structure. Very nice, but again, it's actually not so fast. Maximum 10 to the 5 voxels per second, and feature sizes are at the moment 100 microns and larger than that. Okay, why am I telling you all of this? If you want submicron feature sizes, then there are not so many technologies left. Of course, one is two-photon 3D printing, which I'm emphasizing. There are a few other things out there too, electrohydrodynamic printing, some atomic force-based stuff, but there you talk 10 voxels per second or so. You have to be really patient, or if you have more patience yet, then you can use electron beam induced deposition or ion beam induced deposition of materials, and there you're talking less than 1 voxel per second at the moment. So if you want to go to any reasonable speed at the moment, the only option out there is two-photon based 3D printing. And now I come to these ends here. This is the number of foci that are used in parallel in these publications. So if you're a nanoscribe friend, this is good old nanoscribe technology, this data point here. It gets you some 10 to the 5 voxels per second with some submicron feature sizes. But then the weird thing is that there are data points like this one here where people have used 227 foci in parallel. And you should ask me, am I doing something wrong here? You would expect this should be 227 times faster than using one focus. I have not made a mistake. This is the proper data point. Actually, the individual focus is yet lower, so something went wrong here. You could argue, well, this has been a long time ago in 2005. Well, let's go into Nature last year. Here, this group has used 4 foci. The abstract is full of claims. Well, they have achieved to bring the speed down by 1.5 orders of magnitude and made the resolution worse by a factor of 2 or 3. or so. Yes, that is the achievement. So why is that actually? How can it be that with a single focus you are faster than using multiple foci? And I want to explain this a little bit. Before I do this, let me just re-emphasize that this is a log scale. So if at this speed here, say 10 to the 7 voxels per second, which I'm coming to in a second, something you print takes you 1 minute, then it would literally take you 20 years to print the same thing at that speed here. So we're not talking about details. This is a log scale, just reiterating this point. So how is this story with single focus or multiple foci? What is better? This has been a discussion for years. And this is the simple exercise. Perhaps you just want to listen to my words here, but you can also look at the equations. If you want to scan 100 times faster than some reference to get faster with a single focus, you have to increase the two-photon absorption rate also by a factor of 100 to deposit the same energy, basically. But to increase the two-photon absorption rate by 100, you only have to increase the power by the square root of that, that is by 10. So you can go 100 times faster, but you only need 10 times more power if you do it by fast scanning of a single focus. In contrast, if you want to go 100 times faster by going from one focus to 100 foci, you will need 100 times more power. So it's simply a power issue. Actually, if you are not limited by scanning speed, the best thing is to do scanning with a single focus rather than multiple foci, rather than projection-based. It's the best thing to just scan a focus as fast as you can. Or in other words, this crazy diagram puts this in graphics here. These are lines of constant exposure dose. You just need some cross-linking density that you need to create. I plot this for a certain printing rate I want to achieve. And basically what you see is there are different solutions to this problem. You can pick any of these solutions, but you see they have different powers that you need. Same point that I made before. So you can do things by fast scanning of a focus with low power, or you go to very many foci here, and then you don't need to scan the focus so fast, but you need more power at the end of the day. And what is the best depends now on your limitations. If, for example, you only have a certain power available, and power is getting an issue these days, we're talking about watts of power that we are now using, then the best thing you can do is use a single focus that has the lowest power that you would need. It might happen to you, though, that you simply cannot scan the focus so fast because of some technical limitation. Well, then you have to go to multiple foci, and the reality is that we are limited by different things at the same time, and that's what I'm going to show you in a second. For the parameters I show you, the best solution is to go to order 10 foci in parallel. Yes, please.
So this is the materials research lecture, and so I just wanted to ask a question about the materials. So
yes.
Nowhere here is anything represented about the sensitivity of the material.
Yes, very important point.
Lifetime for the excited carriers to produce a chemical reaction, and so there's probably some not to exceed scan rate dictated by sensitivity of the material, and there's also then a trade-off with resolution.
Okay, let me try to answer that one by one. Yes, we have put arbitrary units because this power will depend on the sensitivity of the resist. The higher the sensitivity, the lower the power is. So I'm assuming I'm already doing a good job on the sensitivity, not changing that, and then this makes a lot of sense.
So this is actually normalized then? It's not pure laser power, right? It's the efficiency of laser power
yes.
for a given resin.
But of course,
yes.
Great high resolution features, it's helpful to have insensitive resists, right?
No, that is not necessarily connected to my understanding. Let me try to answer a few more questions that were in. So time scale, that's actually a very important point. The way we do this now is that the laser comes by, it initiates, it deposits some energy, and until the reaction, the polymerization reaction is finished, the laser focus is roughly 1,000 voxels further already. We are not waiting for the chemical process to finish at all. We looked at this years ago. The time scale is roughly a few hundred microseconds or so. If you have an impulsive excitation until the polymerization takes place. We looked at that by in situ scattering of light from the developing polymer focus. So it's a real measurement in situ, and that's why I trust these numbers. So we're not waiting for that, and we don't have to wait for that. There is no reason. That's different for other 3D printing technologies. If you use macro printing and you want to print something on here, you cannot. You have to wait for something else to be solidified before you can continue. We are not doing this, we're not waiting, because literally these voxels swim in the monomer. That's basically...
Yeah, but then you have excited states of the molecule, and then there's diffusion of energy too, and then this is also limiting the size of the feature sizes at some point. Right?
That's a discussion maybe we can get into later. This is unclear, to me at least, what the role of diffusion is, and we have to discuss diffusion of what. There are different quantities diffusing around there. Perhaps we postpone that.
Okay.
And another issue is, of course, that even if I want to go 100 times faster, I need 10 times more power, then I have to make sure that the intensity corresponding to that power can be taken by the resist, that it's not exploding or something like that. But we're not at that point yet. You have to use the right resist. Some resist just can't take these intensities anymore. That does happen, but there are other resists that do work under these conditions. So basic point I wanted to make, the answer to the question, is it better to use a single focus or multiple foci or projection, depends on what you are limited by. And my gut feeling is the best thing is to do it with a single focus if you can. Let me show you our latest machine that we are kind of proud of. This uses 9 foci, and we have printed, 3D printed parts of that 3D printer ourselves. Namely, the most important component is a diffractive optical element. That's the fancy word for it. It's a stupid grating at the end of the day that is blazed, that all the energy goes into 9 orders only. You can see a measurement down here. It's an 8-level digital hologram, if you want. You see we have pixel sizes here of 2 microns or so and still pretty steep edges. This is printed with nanoscribe technology because the other printer was not ready yet. It needs this component here. Actually, it's a fairly macroscopic thing. You can see it here on a glass substrate. You send in 1 beam and you get 9 beams out. And I find this kind of cool. And if you have a very good eye, you can see some light apart from these foci. This is plotted on a log scale. It's really not well defined, but it's a fairly high precision. If you have a good eye, by the way, you can see that this focus is a little bit dimmer. And this is intentional because it pre-compensates some other aberration we have in the system, which makes the outer foci a bit dimmer. So this is fairly fancy. This is how this looks in the lab, just in case you care. You can see more from the other side. There are some cool little optics tricks if you care about that. So this diffractive optical element uses diffraction. And as you all know, the diffraction angle depends on the wavelength. But once you use femtosecond laser pulses, the wavelength is not a constant. It changes throughout the spectrum, which means the different colors, the different frequency components of the laser are diffracted into different directions, which is the last thing you want, because that means you completely screw up your focus. So what we do is we have some dispersion compensating telescope here with custom-made lenses that actually post-compensates this angular dependence, such that after all, then all the colors come out in the same direction. If you don't do that, this is never going to work. Apart from that, you see some tricks here. We are scanning these galvo mirrors so fast that we have to water cool them. The electronics has to be water cooled because we're putting a lot of power to modulate the beam so fast. In any case, that's how this instrument looks like. And I want to show you here one structure as an example. Forget about this. This is old stuff. This is some stuff we published 2 years ago or so, some fancy 3-dimensional structure. Never mind the function, I talked about this yesterday. This took us about 1 day with nanoscribe instrumentation to 3D print 500 of these unit cells in this structure here. 1 day, 500 unit cells. And this is now what we do with this new generation of instrument. This does not have 500, but more than 100,000 unit cells in it. It took 2 days to print this thing. It's about 1 centimeter in height. You can barely see the unit cells on this picture. You can see it by the lower diffraction. It's a crystal, so it diffracts light as you would think. If you blow it up as much as I can here, you can perhaps see the unit cells and you get an impression about the quality of this thing. So this is about a factor of 100 faster than standard nanoscribe instrumentation in terms of voxels per second. This thing has a crazy high number of 300 billion voxels in it. That's the largest number I have seen. There was a record published in Science last year with some airplane wing that had 5 billion voxels in it. This thing has almost a factor of 100 more in it. And if you zoom with an electron microscope, you see that still the quality is pretty cool, I would say. So I like this very much. Question is, can you go yet much faster? Sorry. And perhaps this comes to questions you have addressed, Harry. One idea you might have is, well, why stop with 9 foci? Take 100,000 foci, or why not just project an entire image into a certain plane and then do sequential exposures? This is actually an important point. This does not work fundamentally. If you go from a single focus to exposing a plane in parallel, then this means that all the photons have to come, more or less, because the absorption is still weak, have to come in at the top, go out at the bottom. In other words, if you want to expose a plane, you get a block. You expose everything. There is no definition in the z direction anymore. You cannot just use projection. And this is the way we do this. First of all, we get rid of two-photon absorption conceptually. You don't need two-photon absorption. You can do this with sequential one-photon absorption processes. Two-photon absorption means that the light induces some intermediate so-called virtual state, but you can take a real electronic state that is there if you switch off the light too. You just have to now tune the time constants that this population is sufficiently weak, and then this population will also be proportional to the square of the intensity, and you gain, if you do that, by the ratio of the lifetime of this state compared to the lifetime of this state. This lives as long as the laser is on, for 100 femtoseconds. This you can tune to live for a fraction of a microsecond or so, and you gain orders of magnitude in sensitivity, and you do not need femtosecond laser pulses anymore. This you can do by a CW laser. These are sequential one-photon absorption processes. And this is a huge difference. If you buy yourself a 5-watt femtosecond laser, it costs you 100, 150, 200K, something of that sort. If you buy yourself a 5-watt CW laser, which is now what we are using, it's about as big as this tip of my finger. 5 watts coming out of this thing, and it costs you 500 euros. 500. It's nothing. That's amazing. We're not doing it like that. We are doing it like this. We intentionally do not go to the middle between these two levels, but somewhere else. And then it's like an AND gate. You have two colors, and you need the blue and the red color at the same time to make this transition. You need this nonlinearity. And that's the way we are doing this. We project a light sheet into a certain plane. This is a trick known from microscopy. And this defines basically a plane into which we print. And then into this plane we project an image. And only if the red and the blue light are on at one location here at the same time, then you do expose the photoresist. And I will not show you any results. This is in progress here. My hope is that we gain another couple of orders of magnitude by doing this, but we will see. This has not been done. I love it because you get rid of the femtosecond lasers, and this scales down the cost and scales down the size and many other things. I'm really slow here. So let me show you a few things concerning multi-material architectures. Let me start with something very simple. And here the idea is basically to use one resist, but change a stimulus during the printing process for this resist. Change the laser power, change the wavelength, change some electric field that you apply or something like that. There are different possibilities, and as a result of this changing stimulus, you get different properties of the material. And these can be drastically different properties. This is a simple example from last year where we took a hydrogel and we used power as a stimulus. We added a cross-linker, for those of you who care, such that by the laser power we can change the cross-linking degree by a lot, really. And what we printed here is two different powers. You can see it here. And then we change temperature as indicated here. And you can see that you don't get small effects, but you get huge effects. And if you calculate this backwards, the Young's modulus of these two parts is different by more than a factor of 10, and so is the expansion coefficient. It's also different by more than a factor of 10. So we're not talking small changes here. This is a huge change, and as a result, this thing acts like a bimetal beam. It's not a metal, it's a bimaterial, a bihydrogel beam, basically. So this works in water, I should say, and only in water. And you can also induce it by light, by two-photon absorption. You induce a little bit of heating locally by light. And this is a real-time movie here showing you different games. It's a bit hectic at times here, so it's not super fast, but it's fast enough for biological applications that we have in mind here, tickling cells or so, or using it in a microfluidic environment. I keep saying this is very nice, but I'm not waterman. I'm not so much into water. I like to do things under ambient conditions, and this particular example does not work under ambient conditions, but we are now working on things that we hope give us similar effects under ambient conditions. Again, by using a single resist, changing some stimulus, wavelength, or some quasi-static electric field, and then writing one resist, giving you different material properties at the end of the day. Very simple trick. If you wonder how reproducible this is, well, pretty much these guys are all doing the same thing here. I don't know, this takes you a minute or two, maybe less, to write one of those guys. This is nothing, really. So very simple stuff, and you can do more complex things too. Let me show you this here. This is now really using multi-materials in a microfluidic environment inside of such a 3D printer. And let me give you the way how we got there. This is a collaboration with Zeiss. And this started with the observation that many security features out there are based on fluorescence. Like in the German passport, you have all these beautiful colors that you see if you UV illuminate your passport. If you go through the passport, it's very colorful. Each page is different. It's a nice security feature. And the name of the game in this community is that there's one group of people who are trying to protect goods, credit cards, passports, medication, or whatever. And there's another group of people, sometimes referred to as criminals, who try to fake this thing, to copy it. And it's a race between these two communities. The good guys try to be a little bit faster and a little bit better, use more advanced technologies such that the bad guys cannot yet do it, and next year you have to do something else. And this brought us to the idea, why not make three-dimensional security features, fluorescent, deterministic fluorescent security features that you could then read out by confocal microscopy. And that's how Zeiss got into the boat here. And this is one of the early designs. The idea is very simple. You take, for example, a non-fluorescent backbone shown in gray here, and then you have fluorescent blobs here that you fix, and you can do whatever you want. And at the end, you can use this as a security feature. The thing is, this is a somewhat painful process. So you go to your nanoscribe instrument, you put a drop of the photoresist, stick it in, do some writing, take it out again, you walk to the chemistry room, do the development, you come back, stick it in again. Oh, it's completely misaligned. You align it in 3 dimensions, put a new photoresist drop, do the writing, stick it out again, go to the chemistry room, and I can convince my students to do this 2 or 3 times. This is what we did here, but then it gets really, really hard to do this job. This works. You can do it like that. These are some measurements. These are fluorescent stacks I'm showing you here. Very imaginatively, we have imprinted a 1 in layer 1, a 2, 3, 4, 5. You can do anything. We intentionally took a dense array here, which is the hardest exercise. You can do it with 2 colors. If you care, we have mixed, in this case, cadmium sulfide, selenide, core shell quantum dots into the resist. You can never bleach these things. If they're in the resist, they are damn stable, really. So this is a 2-color version of this thing, and you can make it a bit more secure. But again, the point here is you need different materials, you need different resists, and at some points this is really getting a pain in the neck if the number of resists is increasing. And this brought us to the idea, why don't we get rid of the chemistry room and integrate that in the form of a microfluidic chamber that fits into this focus condition. That's the hard part of it. You don't have much space to put this microfluidic chamber. You need a glass window. The glass window must not be too thick, because otherwise you cannot get high-end focusing conditions. On the other hand, you want to make the glass window fairly thick because you have to push these very viscous liquids. Some of those are more viscous than honey. You have to push them by pressure through. So if you have too high an excess pressure, your window will explode literally. So it's not a trivial exercise, but what I want to show you, it works. You can take advantage of all the tricks of microfluidics that you can buy. In this case, we used 7 different chemicals inside of the printing process, 5 different photoresists and 2 solvents. This is acetone here, this is, I believe, isopropanol or so. You push these liquids through, and that's the magic part. You can have this microfluidic chamber. The nanoscribe lovers will see that this fits into a nanoscribe instrument, actually, this little thing here. Just squeeze it in, and then you come with a first liquid, second liquid, etc. And it's reusable, of course. You can disassemble it. You're printing on one window, and then you take it out. The thing is, you literally do not need a chemistry room anymore. Everything is done inside of this microfluidic chamber, including the development. This I was a bit scared about in the beginning because I was afraid that you would need some turbulent flow of the developer to really wash out all the parts. And here the Reynolds numbers are so low that everything is laminar. It's 100% laminar flow, but still there was no problem, and you can nicely develop things. And perhaps I'll show you this example. There's a bit of a crazy pattern here. You see in the top row the design, just some colorful thing. These are real colors. These are 4 different fluorescent colors, red, green, blue, and this orange thing here. And this is what we measured in the different planes. It's a 3-dimensional structure, again measured by confocal laser scanning and microscopy. It's even more fancy. In this case, we have put in different colors here on the different blobs, and it just works like a charm. And if you want more materials, that's not a problem. You can scale this up to any number that you want. And I would say this makes a lot of sense if you want to have 3, 4, 5 or more different materials in one structure. Then I don't want to go back and forth between the 3D printer and the chemistry room so many times. This is just very beautiful. If you care, by the way, we have been freely giving this to anybody who wants this stuff. We're not selling this. Nanoscribe is not selling this. So if you care, we're happy to provide you with this. I'm ridiculously slow, so perhaps
You can take 2.5 more minutes.
2.5 more minutes. Let me just make the connection to metamaterials, perhaps, and then I leave away the example here. So where do metamaterials come in here? If you open up your inkjet printer at home, which I have to do a lot because the cartridges tend to get empty, you will find out there are 3 colors, and usually there's black in addition. But you know, by these colors, you can get thousands of effective colors. Actually, I had a misunderstanding for a long time. I thought they were mixing these colors. There's no mixing going on. It's a technique called dithering. It's microstructuring a dot pattern. So you have these elementary colors. You make funny dot patterns, and you design the dot patterns to look like that. And then if you zoom out, you cannot resolve these dot patterns anymore, and it looks to you like a homogeneous color.
Really?
That's how your inkjet printer at home does it. And that's actually, I would say, like a metamaterial. It's a microstructured pattern of dots. And now what we are doing is basically we just make 3-dimensional microstructured patterns such that when you zoom out, you get effective properties that are different from the properties that you have put in. That's the way I think about this. Sometimes I've called this the meta-ink idea. And I think there metamaterials can have an importance. Same thing as dithering, just in 3 dimensions. So I just skipped this example here, just scroll through this to come to the end. I had 2.5 more minutes. This is just some crazy structure, if you care, that we love. Let me just show you that movie. This is a structure that has a negative effective static compressibility. If you find that weird, you expose it to an increasing hydrostatic pressure by a gas or by a liquid, and any ordinary solid would contract, of course. You push on it from all sides, it contracts. What else can it do? This is a positive compressibility in the usual jargon. This thing does exactly the opposite, if you care. If you increase the pressure, it expands. This is outside of my 5 minutes, 2.5 minutes. So let me just get to the end here. I want to say a few words. This is in collaboration with a lot of groups that I'm not going to read to you. We enjoy very much collaborating with chemists over the years, with theorists. All kinds of people get crazy funding for this. And with this view graph, I hope I'm just stopping. Thank you very much.
This is fascinating, absolutely fascinating. So I hope you all have some questions, and soon I'm sort of still in awe from everything that you showed here. Do we have any questions? I'm supposed to be using the mic.
For the coupler which you showed, do you have a number? How much enhancement did you get in the coupling of the light rather than a conventional coupler which we use in our lab? Like you had 3D printed coupler.
This Alphorn coupler, you're asking about the efficiency of the Alphorn coupler. I have to look it up again. It's better than typical grating couplers that would on average give you 10% or so. I know you can get better values, but typically you get something like 10% from a grating coupler. You get more than that, and the big advantage is it's basically wavelength insensitive. You can use it over a very large range of wavelength because it's stupid refractive focusing into a waveguide. It's not using diffraction at all. It's a super simple concept, but it just works.
Any other questions?
So
Yep.
it seems like the most significant feature here, the really amazing thing is finding this material that has a real state because this, as you mentioned, it really has the capacity for dramatically improving the,
Yes.
the writing time.
Yes.
So is that, what was the innovation there? Was it finding a material? How do you go about finding the material that has this characteristic?
Well, first of all, you're asking about how did we find this this photoinitiator? Actually, the resist. The monomer is pretty much normal. It's a special photoinitiator that you're using. How have we found this? Well, first of all, this is a super simplified picture I'm showing you here. The real thing is more difficult. You go from the ground state manifold to the excited state manifold. You go to the triplet, and then perhaps your triplet state lies below some other energy that you need, such that you have to kick out the electron from the triplet state before you start a reaction. That's the spirit. I will not tell you exactly how we do this because it's not published yet. There are two versions we have found so far that do work. So let's see how far this carries that. But even beyond this light sheet printing, if somebody puts some effort into this and makes just a different resist for a nanoscribe instrument based out of this, it could be very much more sensitive than other resists. People have not put any effort into this because this is what is typically called a bad resist.
Exactly, yeah, I was saying insensitive resists are usually.
Yes, you don't usually want that. I mean, normally you want some reaction after a photon has been absorbed. That's exactly not what I want here. I want nothing after one photon absorption. Then I kick it out, and then I get something. This has not been looked at a lot. If you dig in the literature, there are some papers that have looked at that for holography in that context. So let's see.
So are people looking into this now? Or are you the only
We are
people
looking
who
into
you're
this.
looking
I'm
into
not
this?
aware of anybody else
Anybody
looking.
else? All right, any more questions? Go ahead.
Is it possible to have, like, I don't know if it's, I'm far from the chemistry field, but is it possible to, like, selectively erase or delete or take it away on the photolithography process? Not washing by etching or any other process?
Yes, that's the idea of stimulated emission depletion to de-excite certain states. That's what Stefan Hell got the Nobel Prize for in terms of optical microscopy. You can use the same tricks in lithography here. I just left this part completely away because after 10 years of working on it, the bottom line is we have gotten better by a factor of 2, which is nice. But the price of the instrument and the price you pay in the lab is very high. I mean, it's getting much more complicated because you have different foci that you have to co-align to 10 nanometer precision in 3 dimensions. It's getting a pain in the neck. If we had gotten a factor of 10, I would be probably happily selling this to people. But to charge somebody twice the price for getting better by a factor of 2 does not sound like a good idea to me. That's why we didn't do that. That's a super short version of this long story. But again, it's a question of chemistry and of the resists. If somebody has a good idea how these optical depletion or de-excitation things work, you can become famous, I would say.
Yeah. This is all new, the speed. This is the improvement in the speed of writing that you're demonstrating here. Is that commercial already?
No, this has nothing to do with nanoscribe. That's something we did in the lab. I don't know what nanoscribe is going to do.
So
after we have been giving some talks, people have asked nanoscribe, so perhaps they do this.
Maybe there's a macroscribe budding.
I don't know. It's not super trivial to insert that into an existing instrument because you have to do this dispersion compensation. Again, fundamentally, the diffraction angle depends on wavelength, and you have to compensate this, otherwise you get completely screwed up foci.
Any questions from the back there? Maybe some students have some questions?
Yeah,
Or comments? Is it?
please.
I mean, just like from the start, I was kind of confused about the difference between, this 3D nanoprinting versus like lithography, and maybe like, how does the cost of the equipment compare, and like, what are the different options?
Sorry, I'm not sure I understood the beginning of your question. You were confused about the difference between 3D printing and lithography?
Yeah.
That's what you said? That's just a different word for it. To be honest, years I went around selling this as direct laser writing or as two-photon lithography. And that's fine, that's a correct statement, but my experience is that then the reaction of people is, oh, very interesting, but what is it really? What can you do with this? And then at some point we switched to calling it 3D printing, and then people, it's a micro or nano version of macro 3D printers, and it just became clear what this thing is doing. It's just a different word. There's no actual difference. You were asking about cost? No cost.
Any comments? Questions?
Well, cost is actually, it's interesting. We put a lot of effort into this to make three-dimensional structures. That's what I thought would be the kick of this thing. And today I see quite a few groups using or misusing nanoscribe instrumentation to write two-dimensional patterns, happily, because they realize that very often you don't need 10 nanometers of your electron beam writer, and many people are misusing their electron beam writer to write micron-sized patterns with it, and that you might as well do with this thing, and that is a hell of a lot less expensive than an electron beam writer. And I've been using electron beam writers a lot. It's also much more reliable. There's no vacuum, there's no high voltage. That's what typically fails.
Okay.
So it's cool, but
A lot of the materials that you showed us that have a multifunctional response. So you're able to design your materials and then to fabricate like the hydrostatic pressure. That's beyond the negative Poisson's ratio that you were
Yes.
describing. So is that an effect you were intending to
Yes.
Elicit, or
Yeah.
that you discovered it?
no, I mean,
So you wanted to
I
design
didn't
that.
tell you how this thing works. That no way you'd stumble across that by chance. This was actually designed. There's a long history how we came to doing that. Frankly, what motivates me is if people tell me something is not possible. Then I start thinking about it. Well, maybe it is. And this is how this story started. Actually, I've been saying this myself in many lectures in thermodynamics, that it's impossible to get a negative compressibility because it's unstable, violates energy conservation, and blah.
Yeah, right.
I'm not saying this anymore because there are subtleties.
You're willing to.
You can make materials that actually expand if you push on them. Sounds
No,
weird,
was it
but
Graham Milton calculated a certain structure and you made it, or how did you compute?
no, that was
mathematics?
actually us. That was
Okay.
our idea.
That's very impressive. Okay, anyone else? Monopolizing? No? Okay. Let's thank Professor Wegener one more time. Thank you so much.